This 700-ton ball of steel is the only thing stopping a 100-story skyscraper from snapping like a twig in the wind. To the average tourist looking through the glass floor of the Taipei 101 Observatory, it looks like a massive piece of modern art. But to a structural engineer, it is a masterpiece of life-saving physics. This is a tuned mass damper, a device that acts as the building's counterweight, fighting against the invisible forces of nature.
When we look at the skyline of a modern city like New York, Dubai, or Shanghai, we see monuments of glass and steel that appear completely frozen in time. They look unyielding. However, the secret to their survival is the exact opposite. If a skyscraper were perfectly rigid, it would be a disaster waiting to happen. In the world of civil engineering, rigidity is often a precursor to catastrophic failure. The taller a building gets, the more it has to behave like a living organism. It has to breathe, it has to flex, and most importantly, it has to move. The primary enemy of a super tall structure isn't gravity. We've perfected the art of fighting gravity centuries ago. The real enemies are lateral forces, specifically wind and seismic activity. As a skyscraper climbs into the atmosphere, it enters a zone where winds are much stronger and more consistent than at ground level. These winds don't just push against the building, they create a phenomenon known as vortex shedding. As wind flows around the sharp or curved corners of a tower, it creates swirls of low pressure on the opposite side. These vortices pull the building toward them. If the frequency of these wind gusts matches the natural frequency of the building, you get resonance. This is where the skyscraper begins to sway back and forth with increasing intensity, eventually leading to structural fatigue, or in extreme cases, total collapse. This is where the physics of skyscraper design becomes a game of energy management. You cannot stop the energy of a hurricane or an earthquake. You can only hope to redirect it. This brings us back to that 700-ton golden sphere. In the context of skyscraper physics, this is a tuned mass damper, or TMD. Its job is simple in theory, but incredibly complex in execution. It must move in the opposite direction of the building's sway to dissipate kinetic energy. To understand why we need these massive weights, we have to look at the internal skeleton of a giant. Modern skyscrapers use high-strength concrete and structural steel, but even these materials have limits. When a 500-meter tower sways just 2 or 3 meters at the top, the people inside start to feel it. It's not just about structural integrity, it's about human comfort. If the office workers on the 90th floor are getting motion sickness every time there's a thunderstorm, the building is a commercial failure. The tuned mass damper solves both the safety and the comfort problems simultaneously. Let's look at the mechanics of the Taipei 101 damper, which remains the most famous example in the world. This sphere is composed of 41 layers of solid steel plates, each 125 millimeters thick, welded together to form a ball 5.5 meters in diameter. It is suspended by 8 thick steel cables from the 92nd floor down to the 87th. Now, imagine a massive earthquake hits Taiwan, or a typhoon approaches with 200 km/h winds. As the wind pushes the tower to the right, the law of inertia keeps the 700-ton ball in place for a split second before it begins to swing. Because it is tuned to the specific frequency of the building, it swings to the left exactly as the building moves to the right. This out-of-phase movement is the key. Beneath the sphere sits a series of hydraulic bumpers, known as viscous dampers. As the giant ball swings, these cylinders act like the shock absorbers on your car. They convert the massive kinetic energy of the swinging mass into heat, which is then dissipated into the building structure. In essence, the ball absorbs the punch from the wind, so the building doesn't have to. During a major earthquake in 2022, the Taipei 101 damper moved roughly 30 centimeters. It might not sound like much, but that 30-centimeter shift represented thousands of kilojoules of energy that didn't go into snapping the building's support columns. But how do engineers tune a 700-ton weight? This is where seismic engineering becomes a high-stakes math problem. Every building has a natural frequency, the speed at which it naturally wobbles if you were to give it a giant push. Engineers calculate this frequency based on the building's height, weight, and the elasticity of its materials. The tuned mass damper must be calibrated so that its own swinging frequency matches the building's frequency. If the tuning is off by even a small percentage, the damper could actually make the sway worse, acting like a child on a swing being pushed at the wrong time. While the solid steel sphere is the most iconic version, it isn't the only way to stabilize a giant. In some buildings, like the Burj Khalifa in Dubai, engineers took a different approach. Instead of a single massive weight, they used aerodynamic shaping. The Burj Khalifa's buttressed core and stepping design are meant to confuse the wind. By changing the building's shape as it goes higher, the engineers ensure that vortices cannot organize themselves into a single powerful force. There is no single frequency for the wind to latch onto. However, in many ultra-thin pencil towers, like those on Billionaire's Row in New York, space is at a premium. You can't always fit a massive steel ball in the middle of a luxury penthouse. In these cases, engineers often use liquid column dampers. Imagine a giant U-shaped tank filled with hundreds of tons of water. As the building sways, the water sloshes from one side of the U to the other through a small opening. The friction of the water moving through that opening provides the damping effect. It's an elegant solution that uses the building's fire suppression water supply as a structural safety device. The history of the tuned mass damper is also a story of narrow escapes and engineering evolution. One of the most famous cases in civil engineering history involves the Citicorp Center in New York City, built in the 1970s. It was one of the first skyscrapers to feature a TMD, a 400-ton block of concrete. Shortly after it was completed, a student pointed out a potential flaw in the design. The building had been built using bolted joints instead of welded ones to save money, and calculations showed that a once-in-50-years storm could exert enough diagonal wind pressure to topple the tower. The only thing keeping the building standing was the tuned mass damper, but there was a catch. The damper required electricity to operate its hydraulic systems. If a massive storm knocked out the city's power grid, the damper would fail, and the building would likely collapse onto the streets of Manhattan. This led to a secret middle-of-the-night repair operation where teams of welders reinforced the entire building skeleton while the public remained completely unaware of the danger looming over their heads. It was a wake-up call for the entire industry. It proved that these dampers weren't just extras or add-ons. They were integral, load-bearing components of the skyscraper's identity. Today, the technology is moving toward active damping systems. While traditional TMDs are passive, meaning they only move when the building moves them, active systems use sensors and computer-controlled motors. These sensors detect even the slightest vibration from a distant earthquake or a gust of wind before the building even begins to sway. The motors then move the mass proactively to cancel out the motion. This allows for even thinner, taller, and more daring designs that were previously thought impossible. We are currently living in the era of the mega-tall skyscraper, buildings exceeding 600 meters. At these heights, the physics of structural integrity becomes a battle against the fundamental laws of motion. We are no longer just building boxes. We are building dynamic systems that must interact with an increasingly volatile atmosphere. The tuned mass damper is the silent guardian of this ambition. It is a reminder that in engineering, the solution to a massive problem isn't always to stand firmer and fight harder. Sometimes the solution is to find a way to swing with the wind, using gravity and inertia as your primary tools. When you look up at a skyscraper like the Steinway Tower in New York, which is the world's most slender building with a width-to-height ratio of 1:24, you are looking at a miracle of seismic engineering. Without its massive internal dampers, the building would be uninhabitable. It would sway so violently in a standard breeze that it would eventually crack its own concrete core. The engineering behind these giants proves that we don't just build to defy nature, we build to negotiate with it. Every time you step into an elevator in a high-rise, remember that high above your head, hundreds of tons of steel are hanging in a delicate balance. They are waiting for the wind to strike, ready to move so the building doesn't have to. It isn't magic, it is the calculated, deliberate application of physics. It is the art of making the heaviest objects on Earth move with the grace of a pendulum, ensuring that even as the world shakes, our greatest monuments remain standing. The next time you see a skyscraper swaying in a storm, don't be afraid. be impressed, because that movement is exactly what was designed to keep you safe. The pendulum of giants is always at work, balancing the scales between architectural ambition and the raw power of the natural world. In the high-stakes world of civil engineering, the goal isn't to be the strongest. The goal is to be the smartest. And as long as these 700-ton steel spheres continue to swing, our cities will continue to reach for the clouds without fear of snapping.